In today's class, we will be learning about oxidation of an alcohol. And we have used 9-fluorinol because of its ability to do conjugation. And this conjugation will help you see this substance on a TLC plate. It will be UV active because of all this conjugation. Broadly speaking, what is oxidation? Oxidation is just gain of oxygen and loss of electrons. And in today's experiment, we will be learning about both of these steps. One of the first things that you must memorize is the role of each and every salt, starting material, and all the physical steps that we are going to do in this very experiment. So you don't have to worry about creating bleach because this will be available to us as the commercial, the household bleach that we are using. Sodium hypochlorite, or bleach as we will be now referring it to, has several molarities, but for this particular experiment, all of you should know that you have 1.11 molar molarity of bleach. Now, in this particular experiment, oxidation is going to occur. And how? Our catalyst is acetic acid. In presence of this acetic acid, a special intermediate is formed. Now, this intermediate is highly reactive and is generated in situ, which means within the reaction. You cannot isolate HOCl and add it later on. It has to be generated within the reaction. A very special feature of HOCl is that this will give you a chlorine ion. Usually, whenever you see a chloride, its ion would be negatively charged. But this ion is positively charged. So as I was telling you earlier, oxidation is increase in oxygens, but loss of electrons. So this electron deficient species will gain electrons from somewhere. Where will it gain electrons from? From our alcohol. When this electron deficient species, HOCl, will gain electrons from your alcohol, it will oxidize the alcohol. And of course, in the process, what will happen? It will itself get reduced. Furthermore, in this reaction, once your catalyst and bleach has generated the HOCl, it will behave as a nucleophile. Nucleophile overall is an electron-rich species. Remember, the chlorine is positive, but the nucleophile is electron-rich. And hence, this nucleophile will attack your carbon. This is your electrophilic carbon. Why? Look at this polar bond between carbon and oxygen. Oxygen is a positively charged species. How did this get positively charged? Remember, this is an alcohol. Alcohols are a bad leaving group. So you have to make this a good leaving group. In presence of acid, you will get protonation. of your alcohol. So this protonation has caused this carbon to be even more electrophilic. The nucleophilic part then attacks this electrophilic carbon. When this electrophilic carbon is attached, and this is one of the probable mechanisms, the oxygen from the bleach forms your next double bond. Whatever happened to the original oxygen over here, it will be lost as water molecule. So it is the bleach which is providing you with your new oxygen forming your ketone. Overall, what has happened? The alcohol has lost 2 electrons. And instead of having just one bond with oxygen, carbon now has 2 bonds with oxygen. So there is a gain in oxygen electron atoms also. So oxidation, gain of oxygens, loss of electrons. Going further, just remember, instead of fluorinol, we can give you any other alcohol also. So for example, I can give you a molecule like this. And now when I will use bleach, acetic acid, these are the 2 major components of your oxidizing. If you have a solvent, if you have other temperature conditions, those are secondary. What will be the new product that you will show me? You have to remember that this carbon will get oxidized. And so the rest of the molecule stays the same. This carbon right here will get oxidized. So you will form a ketone from this secondary alcohol in a manner like this. Similarly, what if I have a different alcohol? What if I have a cyclohexanol? Again, using the same bleach and acetic acid conditions, I will be generating what? HOCl. This is a very reactive species. This is going to protonate the oxygen, and then the nucleophilic part will attack this electrophilic carbon, forming a ketone right here. So it does not matter what kind of alcohol you will be given, you will be required to show oxidation of those alcohols. During this experiment, we also used workup conditions. So let's just assume that you have this cyclohexanol, which you oxidized. These are going to be your side products. In the same manner, I could have fluorinol, with all of these reagents, and instead of cyclohexanol, I would now have fluorinon. rest of my materials stay the same. So why do we add the sodium thiosulfate? Before that, we always do our potassium iodide test. This test, when conducted on a strip of potassium iodide strip, will give you a black color or a black dot. We make sure at this point that sodium hypochlorite is our reagent of excess, and our alcohol should be gone by this time. So if this test comes out to be positive, we know that our bleach still stays and our alcohol has been eliminated from the reaction mixture. Once you get this test positive, you then add sodium thiosulfate. What is the purpose of this? This is a reducing agent. The reducing agent will react with the oxidizing agent, and it will quench the bleach also. So we know that our alcohol is done. We know our bleach is done. What else is left? Acetic acid, our product, and NaCl and water. Fortunately for us, NaCl and water are water soluble, and hence they will dissolve in water and form the aqueous layer. On the other hand, we will then add sodium bicarbonate. This will help neutralize the leftover acetic acid. Once that is done, we are only left with our pure product in the organic layer, while your other materials will be in your aqueous layer. In the separatory funnel, when you will separate the organic layer and aqueous layer can be separated. Depending on which organic layer are you using. Are you using hexane? Are you using MTBE? All the organic solvents whose density is less than water's density, they will float atop, and then the water layer or the aqueous layer will float at the bottom. Which will you collect? You need to collect the organic layer where your ketone will be present. If you have to locate about the NMR of this structure, how would we differentiate based on that? And hence, a OH peak will appear in your proton NMR. That peak will be absent in your product. You will also see this sp3 carbon hydrogen peak as a singlet. Of course, this is also a singlet. This hydrogen will also be a singlet. No neighbors around it. That peak would also be absent in your proton NMR of your product. In your carbon-13 NMR, beside having the aromatic peaks, you will see sp3 CH peak between 0 and 60 ppm. That peak would be absent in your product's structure. However, a peak that would be present is the carbonyl peak, somewhere around 200 and 225 ppm for your product. Looking individually at their IR, what is the IR differences that you can observe? First of all, in the IR of your starting material, you will see the OH peak. OH peak is round and broad, and it appears between 3200 and 3600 centimeter inverse. That peak will be absent in your product. Another peak that will evidently explain if you have an alcohol or not is your regular C single bond O peak, which appears between 1000 and 1300 centimeter inverse. That peak will be absent in your product. You will also have sp3 CH peaks between 2800 and 3100. Note for fluorinol and formation of its fluorinon, we do not have any sp3 carbon hydrogen peaks in the product. But what we do have are the sp2 carbon hydrogen peaks, which is not a very good feature to distinguish the two of these products. OH, C single bond O, and the C double bond O peak in your product. These are your three differentiation marks or differentiating peaks of IR that can help you decide which is which structure. Once you have your materials in the separatory funnel, your organic layer is at the top and your aqueous layer is at the bottom. You will drain out the aqueous layer in any beaker and keep it aside. You will take your organic layer in a special vial. You can label that as V1. Tilt it, and at the bottom, you will see the water droplets collected together. You can pipette it out by keeping this as tilted. Take out as much as possible, and then add pinches of sodium sulfate in this vial after you have removed the water layer. Wait for 5 minutes. Meanwhile, get a fresh pipette, get a second vial. This vial has to be pre-weighed. You should weigh it out when it is empty, so that with a fresh pipette, you will only collect the liquid from V1 and transfer it to your pre-weighed vial V2. With this, you will only be getting your product, your pure, clean product.